A research engineer is testing the effectiveness of the braking system of a car when it's driven in wet conditions. The engineer measures and records the braking distance, d meters, when the brakes are applied from a speed of v kilometers per hour. Graphs of d against v and log d against log v are plotted, shown below. Explain how figure 6, the log d versus log v1, would lead the engineer to believe that the braking distance should be modeled by this formula here. So it's d equals some constant times v to some power. It's not an exponential, it's one of those like polynomial sort of ones, but there's no extra terms to it. So k and n are constants, and k we need to show is approximately 0.017. All right, this is all about transforming an equation into a log equation. So if I make a start with d equals k v to the n, then we can take log of both sides. I'm doing log to base 10 here. I don't need to, they've written base 10 just to clarify it, but we don't need to, it's implied. So that will be log k v to the n. And I can separate that right-hand side to log k plus log v to the n. Actually, it then becomes log k plus n log v. This, in fact, is in the form y equals mx plus c. This is my y that I've plotted along the y-axis. This here is my x, this is my m, and this is my c. So because we get a straight line in figure 6, that is enough to say that the distance can be modeled by that formula. So I said log d versus log v should be a straight line. And it is. So result follows. Just need to show that k is approximately 0.017. So we've got this point here, that's my y-intercept, that's going to be log k. Log k is going to equal minus 1.77, which means k will be 10 to the power of minus 1.77 when I undo the logs. Which gives 0.01698. Which I can then say k is approximately 0.017. Then asked, using the information given in figure 5, that's this point here, with k equals 0.017 to find a complete equation for the model giving a value of n to 3 significant figures. So when v equals 30, d is equal to 20, and I can sub that in to here. That is the most direct one to use. Therefore, I'll get log 20 is equal to log 0.017. We actually know the exact value should be minus 1.77, but it's asked us to use this value, so I'm going to stick with it, plus n times log 30. So I can do log to base 10 of 20 minus log to base 10 of 0.017, and then divide that by log 30. This gives 2.0787. So finally, d is going to equal 0.017 v to the power of 2.08. No, I could have subbed in to this formula directly, including my k, but then I would have had to have taken logs. You know, it's actually would have taken a bit longer than just putting it into the log equation. So that's why I went with this method. Finally, we're told that Sean is driving this car at 60 kilometers per hour in wet conditions when he notices a large puddle in the road 100 meters ahead. It takes him 0.8 seconds to react before applying the brakes. Use the formula to find if Sean will be able to stop before reaching the puddle. So this is our formula. This is actually the breaking distance. And there's also a thinking distance for when his reactions essentially from seeing the puddle to starting to break. Let's work out the breaking distance first. So V is 60. That means D is going to be 0.017 times 60 to the 2.0. Now, I'm not going to use the rounded one. It's always best practice to use the non-rounded, so 787. Otherwise, you can lose accuracy in your third significant figure. So 0.017 times 60 power 2.0787. I know I've rounded it here, but it's gone beyond the three significant figures. That gives 84.467. Now we've got to think about the thinking distance. Well, it's going to be speed times time, but they're not in the same unit. At the moment, I've got seconds and hours, and also we want to know the distance in meters. So I'm going to change kilometers per hour into meters per second. 60 times 1,000 gets me meters per hour. Then I need to divide by 60 twice to get meters per second. You could alternatively take your 0.8 and divide that by 60 and by 60 again to get it in terms of hours. Then it would be meters per hour times by a time in hours. That would also be consistent. Either's fine. This gives us 13.3 recurring, which means the stopping distance. I'm using technical words here. Actually, this is in the highway code, but don't stress about it. If you just have to realize to add them together. So stopping distance would be 84.467 plus 13.333. You can see it's going to be less than 100, but let's work out the exact value. 97.80, which is less than 100. And then I'm just going to write a little conclusion. So according to the model, Sean will stop before the puddle.